As a reminder for the probability oh goodness. No. As a reminder for the probability notations we've seen so far. We've seen the probability notation where we just talk about a single event. But when there are two events involved, we actually saw three different probabilities that we need to be able to find. We had our and probability, the two events both occurring. We had our or probability, either of the two events occurring, and we had our conditional probability. So 4.2 really shows us the relationship between all of these and gives us some of the formulas that we're going to be using to find probabilities on the test and in this course. The first of those formulas is this addition rule, and we saw this in class. So every class we came up with this idea of, okay, or I need to take everybody in A, I need to add up everybody in B, but oh crap, I counted people twice. So this is that formula. This is an official formula to do exactly what we did in class of adding the total from A, the total from B, and then subtracting off that intersection, the piece we counted twice. In fact, in our example, this was the 221 people that we counted twice instead of out of like the 370 men and the 325 who are not very happy or whatever, very happy. I don't remember even what our question was, but sort of that. These are generally thought of as the probabilities, so each of those numbers I wrote would have been over 603, but it ends up the exact same. And then we have the Venn diagram here on the side, just so we can visually see what we saw in that contingency table, because a Venn diagram tells us a lot of the same stuff as a contingency table. If we take the probability of A, or all the events in A, we add all the events in B to that, right? Our B, our A. What we have done is that we have double counted all of this intersection, right? We counted it once in A and once in B, which is why we need to subtract it off. So just a visual reminder of what we saw in class on Thursday. So we got our first example here of how this question might come up on a test. And our first example of really translating everything using that probability notation I was talking about. So first thing it makes sense to do is to just read through your question once. So I want you guys to take a moment, read through 4.2.1. Once you have your bearing, you can see right here, we've been given 1, 2, 3 probabilities, and we have been asked for one more. So one of the smartest things to do here is to translate what we've been given and what we're looking for, and then see, does this sweet formula up here help me out? Or what formula on the formula sheet is going to save the day for me? So our events are the first thing we have to decide. And it looks like we have the idea that kittens could be black, they could have green eyes, and then we have green eyes again and black again. So those are our two events. And normally we're only dealing with two events. So as we read through the 30%, the only thing in this section is about the kittens being black, nothing about the color of their eyes. So the probability a kitten is black is just 30%, nothing about green eyes. As we continue on, 75% have green eyes, nothing about having black fur. So the probability of green eyes is equal to 0.75. And 24% have both. Now, both is not the nicest keyword, but it is pretty simple for us. This means that they are black and have green eyes, right? So that's going to be our black and green eyes. And then the last piece, which is frankly one of the most crucial pieces, is what am I asking you for? Because I don't want you to answer the wrong question. What is the probability a kitten selected at random from the shelter will have green eyes or black fur? So that's what we're looking for, G or B. If this were a test question, I'd be looking at my formula sheet. I would see on my formula sheet, I have a formula for or. Let's see if that formula works out for us. So I'm just going to go ahead, and when you use the formulas on the formula sheet for this probability section, it's almost a two-step process. Your first step is to go through and change the formula so it matches your events, since I like to use letters that make sense for my events. So in this particular case, the probability of G or B, same thing as A or B, all I need to do is change every A to a G. So the first probability of A, that's just going to be the probability of G. We have the probability of B plus the probability of G. And then we remember that union symbol, or the intersection symbol, sorry, is our AND, right? G and B. So that's exactly what we have. So that's the first step. Step one, we rewrite our formula using the events that we're actually using in our question. Second piece, plug in things where they go. So probability of green is 0.75. Do not do this. I've seen a lot of students over the years do this, where they only replace the G. This 75% is the probability of G. So there should be no probability symbols when you come down here. It should just be 0.75. Probability of B is 0.30. Oh my goodness, I wrote a plus. That's terrible. Don't do that. It's a minus, right? Follow this equation. And then we need to subtract off our and. And this is the first point where we sort of realize, and it doesn't matter what order we write things in. Black and green is the same as green and black, because remember, we're talking about this intersection here. And in this intersection, it doesn't matter which thing you talk about first. So we can go ahead and just subtract off that 0.24. Oh no, I keep grabbing that big pen on accident. I should have brought a calculator with me because simple math is not my jam right now. That looks like it's going to be 81%. Another thing to just think about as you're doing a question like this, an OR question, remember this Venn diagram here. When we're doing an OR question, if all of G, let's just replace this for a second. Let's just make this cleaner for a moment for me to use for this example. If these are my two events, green eyes and black fur, and I know that green eyes is 75%, that means this entire circle, I intentionally grabbed my big ass pen, is 75%. Both this piece and this piece together is 75%. And if I'm talking about OR, I want, again, I'm going to use a big ass pen, I want everything in either of these, right? So I'm going to have to take 75, I'm going to have to add a little bit more. So no matter what, my answer needs to be something slightly bigger than 0.75, and so 0.81 makes sense in this particular situation. Now we have one more piece to talk about when we talk about this addition rule, and that is the idea of having disjoint events. So by disjoint events, we are talking about things that are mutually exclusive. They cannot occur at the same time. So if you wanted to see a visual representation, you see that in the Venn diagram. Our A circle and our B circle have zero intersection, right? Whenever you see disjoint, this is telling you the probability of A and B is just zero. They cannot occur at the same time. So that means our little rule from above simplifies. Instead of having to subtract off probability of A and B, well, we know that's zero, so we can just get rid of it and instead just add the two events together. My word of caution here is we have these simplified formulas, and we used to give them out on the formula sheet at SDSU. And what would happen is students on the exam would look at the two formulas and go, well, that one's easier, and they would use it even when things weren't disjoint. So I will not be giving you this formula. If you want it, you'll need to write it down somewhere on your note card. But the biggest caution is to only use it if you are absolutely sure that the two events are disjoint and that there's no way they can occur at the same time. Most of the time you will not have to think this through. I will either tell you they're disjoint, or it would just be sort of a common sense type situation. And we'll actually see more of that common sense situation in 4.4. Okay, so we have two questions associated with this addition rule for disjoint events. First one here says, suppose 45% of students have iPhones, 40% have an Android phone, and the remaining 15% have some other type of phone. Assuming a student can only have one type of phone, what is the probability a randomly selected student has a phone other than an iPhone? There are two ways to think of this. One is you could think of this as the probability of not iPhone, right? Or the probability of iPhone complement. And you could just take, okay, well, if 45% of students have an iPhone, that means 55% of students don't have an iPhone. Boom, done. The other way to think of it is what was written here. It could be Android or other. This is all under the assumption that it can only have one type of phone, right? Non-overlapping. That is the key piece. This is what tells us that we're dealing with disjoint events. Since we have that, we could do this as an OR question. This question is also the probability of Android or other. And since we don't have an intersection, we can just add those two things together. It's either Android or other. There's no and between those because they can only have one type of phone. And we could just add the 40% to the 15% that have an other and get that 55%. So just looking at this question two different ways. Last one continues that terrible dice rolling example from the first section that we did on Thursday. What is the probability of rolling two dice that sum to 7 or doubles? Well, if we recall, the probability of A was 1/6. The probability of B was also 1/6. And these two events were disjoint, right? A was all the things that sum to 7. And B was all the doubles. It is impossible to have doubles and sum to 7 because all the doubles are going to have an even sum. So these two events are disjoint. And if I was thinking of either of these being what I was aiming for in a game of craps or whatever game I might be playing with two dice, then I would just go ahead and add the 1/6 and the 1/6 together, giving me 2/6 or 1/3 probability of rolling a 7 or doubles. All right, the last piece on this page is something actually I test quite a bit. So I'm going to put a big fat star next to it. No, I keep grabbing the actual screen. All right, so independent or disjoint events. So we just talked about what disjoint is. Disjoint is mutually exclusive. They can't occur at the same time. Our probability of A and B is 0. You cannot have them occur at the same time. Independent is a little bit tougher. When we talk about independent, this means that one event does not influence the other event. Knowing the outcome of one event does not tell me anything new about the outcome of the other event. So there's no relationship at all. Independent is also no relationship. So an example of something that would be independent would be like flipping a coin. Oops. Flipping a coin and getting heads, right, if that's event A, and event B being that it rains tomorrow. There's absolutely no relationship between the flip of my coin and whether or not it's going to rain tomorrow. So that would be something that is independent. Whereas something that is dependent means that there is some relationship, that knowing one outcome does tell me something more about the other. So an example here would be if it rained today, that might give me more information about whether or not it's going to rain tomorrow, right? It might increase the probability if it is raining today that it would rain tomorrow. To give you another example, I'll switch up this A and B. You guys can keep whatever you want in your notes. My other example here, oops, is the one I always give at this point in the class. Let's say we're looking at gender. Now, if event A is that someone is male, so let's say I already know this outcome. I picked somebody out of the class and I know the person is a male, right? If my event B is whether or not they like pizza, the real question is, okay, well, the probability of liking pizza, let me not write like, let me just write pizza here. The probability of pizza, well, if you came up with your guess, the probability of people in the class who liked pizza, it'd probably be pretty high because pizza is delicious. So let's say it's 90%. This probability, pizza for a male, should be roughly the same, right? Unless you're thinking stereotypically, we generally both genders like pizza the same. So knowing that a person's a male is not going to change my guess that they like to eat pizza, right? It is not giving me any new information. However, on a dependent side, We could still stick with male, but now I could be making up a soccer team, like my soccer team, that wears pink shirts. So the probability that you own a pink shirt, well, we can actually find this from our class. I think this probability was around 40%. It was pretty dang low. And the probability of owning a pink shirt for the males was even lower. This was something around 20%. And we could actually pull this up in StatCrunch to verify this. But the fact that this probability is not the same tells us that having this information that somebody is male has changed my probability that they own a pink shirt. Females, if someone is female, I have a higher probability they own a pink shirt. If someone is male, there's a lower probability. So we have that relationship. So understanding independent and dependent and disjoint and joint, crucial, and something I test in multiple ways on the exam, and you'll see those all. In fact, that first page of your homework, all the stuff from 3.2 and 3.3 focuses on this independent disjoint relationship, every single question. So that homework is your best bet for studying independent versus disjoint. Since this video is getting long, I'm going to cut it here and I'll finish it up in a second video.